recently we talked about the relation between the stability properties of an LTI system and the eigenvalues of the system matrix, the A matrix, okay? I'm talking about the stability in the sense of Lyapunov. In fact, the eigenstructure of the A matrix completely characterizes the stability properties of the system x that equals AX. Now, that method, that tool, which is very, very useful and important for LTI systems, cannot be extended to the nonlinear systems for the obvious reason that nonlinear systems do not have eigenvalues. Okay, but the linearization of a nonlinear system around an equilibrium point does have eigenvalues, and it turns out that those eigenvalues tell us something important about the local behavior of the solutions of the nonlinear system around the equilibrium point at which we perform the linearization. So in this hour, we'll be talking about the relation of the eigenvalues of the A matrix that we obtain from linearization and the behavior of the solutions of the actual system around that equilibrium point. Okay. So we consider the autonomous time-varying case. Okay. In other words, our nonlinear system has the following form: x that equals f of x. X is our vector in Rn, and f therefore is a mapping from Rn to Rn. Okay. X is in Rn. Let's call this system 1. And then this system may have many equilibria, and among all those equilibrium points, suppose that we are interested in one of them, and that equilibrium we indicate by, let's say, x bar. Okay, and by definition, that equilibrium must satisfy the relation that f of x bar equals 0. Okay, so that means x of t identically equals x bar, that constant solution, constant function is a solution of this system. Okay, that's how we define an equilibrium point. Now, whenever we have an equilibrium point, we can talk about the linearization of our nonlinear system around that. And suppose that we perform the linearization of our nonlinear system 1 at the equilibrium point x bar and obtain the following nonlinear system where LTI system where A is an n by n real matrix. Okay. 2, where C is the displacement of the actual state from the equilibrium point x minus x bar, and the matrix A is evaluated through this Jacobian computed at the equilibrium point x equals x bar. X equals x bar. Okay, and right, so that's the linearization of x that equals f of x. Now, the question that we will talk about in this hour is the following: what does the stability or instability of the linearization, okay, which we denote by equation 2, tell us about the stability of the equilibrium of the original system, x that equals f of x. Stability of the equilibrium whose x bar of the original system. Okay. Remember how these solutions of the original system, x of t, and the linearization psi of t were related. If you start your system, okay, somewhere close to the equilibrium point, x bar, okay, so you run the system starting from x0, and then you obtain the solution x of t, and then put that somewhere, record that somewhere, and then you start the linear system from the initial condition, which is x0 minus x bar. So that's your psi 0. So you start your system psi 0 and obtain psi of t from that linearization. And then the relation between psi of t and x of t is such that x of t minus x bar is close to psi of t. Okay, so those two functions are close to one another for as long as x of t remains close to x bar. Okay, so that's the relation between the solutions of the linear system and the solutions of the actual system. Okay, so as far as the actual solution remains close to the equilibrium point, so the linearization can be used as a successful approximation of the actual system. Okay, now here is an important theorem from the stability point of view. Now, since the two solutions are close to one another for a while, so that means the stability properties of this system should tell us something, at least in certain cases, about the stability properties of the solutions around the equilibrium point x bar. Okay, and this theorem formalizes that. Suppose that the right hand side f is differentiable, so that we can talk about a linearization or the Jacobian. If the linearization or the linear system 2 is exponentially stable, that means all the eigenvalues of the A matrix are with strictly negative real parts, then there exist following constants. Okay, all positive, epsilon, c, and lambda, such that x t0 minus x bar less than epsilon. So this means that if initial condition is close enough or in epsilon neighborhood of the equilibrium point, then the solutions converge to the equilibrium point x bar in an exponential fashion. That is, this can be upper bounded by c e to the minus lambda t minus t0 times the initial distance to the equilibrium point, x t0 minus x bar, for all t greater than the initial time t0. Okay, and such equilibrium point of a nonlinear system is said to be locally exponentially stable. Okay, and it means that if you start close enough to the equilibrium point, then the solutions converge exponentially to the equilibrium point. It is called locally exponentially stable equilibrium point. Okay, note that for linear system we don't have to introduce such a concept of local exponential stability, because if you have local exponential stability, then due to homogeneity property of the linear system, then it means that no matter where you start, you always converge to the origin in an exponential fashion. Therefore, for linear systems, for LTI systems, local exponential stability and exponential stability or global exponential stability, they are the same thing, okay, they are equivalent. But for a nonlinear system, they don't have to be. Okay, we're not going to prove this theorem. For those of you who are interested, you can find it in the text or any other linear systems book. Okay, and here is a dual theorem in a sense. So this theorem is about stability, and the next theorem is about instability of the equilibrium point of our nonlinear system. Okay, so this is the theorem of instability. If the matrix A, by which we mean the matrix that's obtained through linearization, has an eigenvalue satisfying this, that is, if the A matrix has at least one eigenvalue on the open right half plane, then there exists an epsilon, okay, such that no matter how small you start to your equilibrium point, the solution, you can always find a solution, no matter how close you start to the equilibrium point, such that that solution eventually, if you wait long enough, eventually gets outside the epsilon ball around the equilibrium point. Okay, such that for each delta, it could be arbitrarily small, nevertheless positive, there exists a time t large enough and a solution of the nonlinear system x of t satisfying the following. Okay, x t0 minus x bar. So distance, the initial distance to the equilibrium point is not larger than delta, okay? What you pick. And then if you wait long enough, okay? By long enough, you mean if you wait for t units of time, then minus x bar is greater than epsilon. Okay, such equilibrium x bar is called an unstable equilibrium. Okay, so once again, no matter how close you pick your initial condition to the equilibrium point, it doesn't say that all initial conditions satisfying that would eventually get outside the epsilon ball. Okay, it just says that if no matter how this delta, no matter how small this delta is, you can always find an initial condition that's in the delta neighborhood of the equilibrium point, such that if you start from that initial condition, eventually you leave epsilon. Okay, so that violates the qualitative definition of stability, which was if you start close to the equilibrium point, you remain close to the equilibrium point, and because of that violation, such equilibrium points are called unstable. Now, before we provide conditions we apply these theorems to examples, let's try to visualize those stability and instability behaviors through some simple sketches.
Okay. So let's first try to visualize local exponential stability. Okay, it says that suppose x bar is the origin. Okay, and we have a second order system. Horizontal axis indicating x1, let's say the vertical axis indicating x2. And this is our phase plane. Now we're gonna provide some example phase portraits. Local exponential stability is such that you can find some neighborhood of the equilibrium point, and for simplicity we're taking to be the origin. Okay, so this is our epsilon neighborhood. Okay, and then all solutions starting in this neighborhood with an overshoot that's proportional to the initial distance to the equilibrium point, and that overshoot is characterized by that constant c. Okay, let's say this is c epsilon. Then, if provided that you start within that ball, epsilon ball, you may leave that ball, but eventually you converge and in an exponential fashion to the equilibrium point, to the origin. Okay, so this is x of t. And this is, let's say, x0, and so on. So this is a very rough picture of local exponential stability. And no matter where you start in epsilon ball, you would always have this convergence and overshoot constraint satisfied for a local exponential, stable equilibrium point. As for an unstable equilibrium point for a nonlinear system. So suppose that this is the ball that we want to remain, okay, for all future times. And for that, what we want is, in order to guarantee that, we want to be able to start close to the equilibrium point, okay. And if the equilibrium point, which we take the origin for simplicity, if it's an unstable equilibrium point, it would mean that no matter how small you pick your initial condition, or okay, that wasn't that right. So this is our epsilon ball. So we want to remain in that ball. How we want to remain in that ball? By starting close enough to the equilibrium point. Now you pick some delta, let's say delta 1. So that's the distance initial that characterizes the initial distance, okay, to the equilibrium point. So for this delta 1, certain solutions starting within that ball may converge to the origin, but there is, let's say, some equilibrium point, some initial condition such that when you start in that from that initial condition, and that initial condition is within delta 1 neighborhood of the equilibrium point. So eventually that solution leaves the epsilon ball. So then you say, okay, perhaps delta 1 is not that small. I should pick something smaller. Okay, delta 2. And then even within that tinier ball, you can find an initial condition, okay, such that starting from that initial condition, and this time you may have to wait a little longer, because smaller the delta, larger the t we would expect, okay, and then you again leave the epsilon ball, and then you squeeze this delta further and further. But no matter how further you squeeze that delta, there exists always some initial condition, okay, such that if you start the system from that initial condition, then eventually you leave the you leave the epsilon ball. And if that's the case for an equilibrium point, such an equilibrium point is called an unstable. Okay. So this is an unstable equilibrium point description. Okay, now let's see some examples. Okay. Where we can apply either this theorem or that theorem to determine local exponential stability or instability. Okay, but if you look closely at the conditions in these theorems, you will see that those conditions, okay, they do not cover all possibilities. Okay, namely, there may exist a linearization such that neither the condition of stability theorem or the condition of instability theorem is satisfied. Such cases are called indeterminate cases. Okay, so let's also talk about them and what can be done for those cases. And then we will move on to other examples. Okay. Indeterminate case. Okay. Now, exponential stability theorem requires that all the eigenvalues of the linearization are on the open left half plane. Theorem on instability requires that there exists at least one eigenvalue on the open right half plane. And then, therefore, there is the indeterminate case where all the eigenvalues are on the closed left half plane and you have at least one eigenvalue on the imaginary axis. If that's the case, then that condition neither fits the stability theorem nor instability theorem, and those cases we call indeterminate. Okay? When the eigenvalues of the linearization satisfy the following. Okay, all of them are on the left, closed left half plane, and there exists at least one eigenvalue on the imaginary axis. Okay, in that case we can neither off the shelf use either theorem. We cannot determine the behavior of solutions of the nonlinear system. X that equals f of x around the equilibrium point. Okay, so this means the following: the eigenvalues in this case will not tell you anything about the qualitative behavior of the solutions of the original system. Okay, let's provide an example to that, to the indeterminate case. Here are some examples for the indeterminate case. Okay. So let me divide these two columns Okay. This is our system, this column, x that equals f of x. This is linearization. At the equilibrium, and our examples will all have equilibrium at x bar equals the origin. And the behavior of the linear system, linearization xi that equals a xi, and the behavior of the original system. Actual system x that equals f of x. Okay, our first example is a scalar system x that equals minus x cube. Okay. Now, the Jacobian is minus 3x2 square. Evaluate that at the equilibrium point 0, which produces 0. So the A matrix, in this case, this is just a scalar, is 0. So that means what we have is xi dot equals 0 times xi, or this is our linear system. Okay. Now, what's the behavior of this system? It's clear. Xi dot equals 0, so that means wherever you start, you always remain there for all times. Therefore, even though you do not converge to the origin, you remain bounded, the solution remains bounded, therefore this system is stable. Okay? We have just one eigenvalue at the origin. The corresponding Jordan block is of size 1 by 1, so we conclude that the system is stable. Okay? In fact, the norm always equals the initial norm for all times. Now, if you look at the actual system through, let's say, a very simple Lyapunov analysis, take the Lyapunov function 1 over 2x2 squared, you'll see that v dot always is negative, so that means Lyapunov function is decreasing and x of t converges to the origin. Okay, so the actual system turns out to be asymptotically stable. Okay. Hence, the behavior of asymptotic stability of the actual system is not catched by the, or detected by the linearization. Okay, because this corresponds to one of to the indeterminate case. X that equals plus x cube. Okay, this time the Jacobian is 3x2 squared, but nevertheless it produces the same A matrix. So that means we have the same linear system, same linearization. Okay, which tells us that the system is stable, although not exponentially stable, it's stable. However, the actual system is unstable. Okay, x of t converges to infinity. In fact, it converges to infinity quite in a wild fashion. Okay, this system is said to exhibit finite escape times. It can be solved explicitly, that differential equation, and this is the solution. X of t equals x0 divided by square root 1 minus 2x0 squared times t. Okay, so in finite time, the denominator becomes arbitrarily large, therefore x of t reaches infinity in finite time. Okay, whereas the behavior of the linear system is very innocent. It's just stable. Okay, let's move on to a little bit more sophisticated examples. Second order systems. x1 dot equals x2, x2 dot equals minus x1 cube. Okay. Again, we're dealing with the linearization at the origin, and the origin is the only equilibrium point for this system. What's the linearization? Xi dot equals, now we expect a 2 by 2 A matrix here because the system is second order. Let's fill in the entries. This is partial f1 with respect to x1, so partial x2 with respect to x1, which is 0. Here we have partial x2 with respect to x2, which is 1. Here we have partial minus x1 cube with respect to x1, which is minus 3x1 square. Evaluated at the origin, that produces 0. And finally, partial minus x1 cube with respect to partial x2, that produces 0. Okay, so this is our linear system. The A matrix is upper triangular, so diagonal entries are the eigenvalues of the A matrix. Both are at 0, and the corresponding Jordan block is of size 2 by 2. In fact, the A matrix is already in Jordan form. Therefore, the behavior of linearization is that this system is unstable. Okay, unstable. How about the behavior of the original system? It's stable. In fact, the Lyapunov function remains constant for all future times, or the positive definite function v of x0 for the following choice of positive definite function, which is 1 over 4 x1 to the 4 plus 1/2 x2 square. Okay, if you compute v dot along the solutions of the system, it's easy to see that it is 0. V dot 0 means v is constant for all future times. And if this thing is constant, this function is constant since it's positive definite, so that means solutions starting close to the equilibrium point must remain close to the equilibrium point. Therefore, the equilibrium point is stable. Whereas the linearization is an unstable system. And finally, x1 dot equals x2, x2 dot equals, let's add a further term, x1 cube minus x2 cube. This produces the same linear system. Okay. Therefore, again, we have instability if we just look at the linear system. However, this system can be shown to be asymptotically stable. Okay. That is, all solutions asymptotically converge to the origin. Okay. So this example, or the negative example, just makes it clear that whenever we have the indeterminate case, that is, whenever the eigenvalue, the conditions or the eigenvalues of the A matrix do not satisfy the conditions of either the stability or the instability theorem, then just forget about the eigenvalues. Okay, so you have to find some other means, for instance, by a clever choice of Lyapunov function or positive definite function, you need other means to determine the behavior of the solutions of the actual system. Okay, now let's see an example where we can apply the theorems of this lecture. So let's revisit our favorite nonlinear example, namely the pendulum. So let me write down the normalized model with friction, okay, of the pendulum. So this is the pivot, this is our pendulum, this is the vertical line, here this is the direction of gravity, and here this is how we measure the angle displacement of the pendulum from the downright equilibrium point. Now here is the model normalized of this pendulum, okay, theta double dot plus epsilon theta dot plus sine theta equals 0. This epsilon theta dot, where epsilon is a positive constant, indicates the friction effect, okay, the energy loss. Epsilon is positive. Okay. Now, for this model, what we're going to do is we're going to obtain the state space representation, okay, x equals f of x, by choosing the state as theta and theta dot, x1 equals theta, x2 equals theta dot. And once we have x equals f of x, okay, we can easily obtain the linearization, okay, at the equilibrium points. Remember, this system has two equilibria. One of them is the downright equilibrium position, and the other is the upright equilibrium position. And we know from experience that this guy is stable and the other guy is unstable. So let's see whether our theorems would agree with our everyday life experience regarding this simple system. Let x1 equals theta and x2 is the angular velocity, theta dot. Okay, this produces x dot equals the following: f of x, where f1 is, okay, what's f1? f1 is x1 dot. x1 dot is theta dot is x2, therefore here we have x2 for our f1, the first entry of f of x. How about f2, the other entry? It corresponds to x2 dot. x2 dot is theta double dot, and theta double dot is minus epsilon theta dot minus sine theta. So in terms of x1 and x2, that can be written as minus sine x1 and minus epsilon x2. Okay, so that's our f of x. The Jacobian of that right hand side yields the following 2 by 2 matrix. Okay, this is partial f1 with respect to partial x1. This is f1, therefore partial x2 with respect to partial x1 is 0. Here we have partial x2 with respect to partial x2. This is 1. Okay, here we have partial f2 with respect to x1, so that makes minus cosine x1, and finally this is partial f2 with respect to partial x2, and that produces minus epsilon. Okay, so that's the general expression for the Jacobian of our right hand side. Now we know that we have two equilibrium points for the system. Equilibria, x bar equals, one of those equilibrium points is 0, 0, that is the equilibrium that's the downright equilibrium point, because we start measuring theta starting from that downright equilibrium point. The other is the upright equilibrium point, which is pi and 0. Okay. Okay, note that at both equilibrium points, theta dot, the velocity must be 0. That's why we have 0 here and 0 here. Okay, so what we're going to do now is we're going to evaluate the A matrix at both equilibrium points and then check its eigenvalues and see whether we can apply the theorems, either the stability theorem or the instability theorem, and reach the possible conclusions regarding our system. Okay, and once again, let me remind you that it's not right to say that the pendulum system is stable or pendulum system is unstable. Stability is not a property of the system. Okay, it's a property of the equilibrium point. So, the grammatically correct way of saying that sentence is pendulum, or the equilibrium point 0, 0 of the pendulum system is stable. Equilibrium point pi 0 of the pendulum system is unstable, and so on. But for linear systems, we don't have to be, in a sense, correct that correct grammatically, because whenever we say a linear system is stable, we implicitly mean the origin of the linear system is stable, or the origin of the linear system is unstable. Okay.
Okay. So let's perform the linearization. So linearization at x bar equals 0, 0. Okay, this is the downright equilibrium position. Okay, now A equals minus cosine x1 minus epsilon. So Jacobian evaluated at x1 equals 0 and x2 equals 0. Okay. The only thing that depends on x1 and x2 is here. We have minus cosine x1. Plug in x1 equals 0, theta equals 0. So this produces what? Minus 1. So what we have here is psi dot, okay, equals 0, 1, minus 1, minus epsilon psi. So that's our linear system, okay, coming from the linearization at the downright equilibrium point. So let's look at the eigenvalues of this linear system, Si minus A. Okay, the determinant will give us the characteristic polynomial, which is S squared plus epsilon S plus 1. So this is a second order polynomial with all positive coefficients. Therefore, the eigenvalues are all on the open left half plane. In other words, this system is exponentially stable. And since the linear system is exponentially stable, that behavior will be inherited locally by the solutions around the equilibrium point where we perform the linearization. In other words, downright equilibrium is locally exponentially stable. It's clearly not globally exponentially stable because you can always start the system from the upright equilibrium position, and if it starts there, it will always remain there, and clearly the solutions will not converge to the equilibrium point 0, 0. Okay, therefore the behavior is local only. Okay, how about the other equilibrium point? Okay. Linearization at x bar equals pi 0, the upright equilibrium position. Okay. This produces psi dot equals, this time we're evaluating this at pi. Cosine pi is minus 1, so we have minus 1. So that means 0, 1 minus epsilon. This entry will be plus 1. Okay, psi. So that produces Si minus A, characteristic polynomial, equals S squared plus epsilon S minus 1. So the product of the eigenvalues is negative, so that means we have to have one real, one positive, one negative eigenvalue, both real. Okay, so that implies there exists an eigenvalue such that its real part is strictly positive. It's on the open right half plane. Hence, we can employ our instability theorem and claim that upright equilibrium position is unstable. Okay, which is what we have expected. Before we close, let's also very briefly mention the analogous result for discrete time, which may be useful at some point. Okay. Now here is the notation regarding the discrete time case. System is represented by this difference equation: x plus equals f of x. Okay, so the value of state at the next time instant is value of the state at the present time passed through this mapping f. X is in Rn, therefore this mapping f is from Rn to Rn. Definition of equilibrium is that if you start at that point, you remain at that point for all future times. So that implies for the continuous time that f of x bar equals 0. For discrete time, however, it implies that f of x bar equals x bar. So that if you start at x bar, at the next time instant, f of x bar, you're at x bar. At the next time instant, f of x bar, again you're at x bar. So it's clear that if this is satisfied, then starting from x bar, you remain at x bar for all future times. And this is the definition of equilibrium point. Linearization. Obtained in the same way. Okay, xi plus equals a times xi, and a matrix is the Jacobian of the right hand side evaluated at the equilibrium point x equals x bar. Okay, so for a given nonlinear system in discrete time with an equilibrium point x bar, this is how we compute or how we obtain the linearization. Okay, xi plus equals a xi. And now the theorems, they can be carried intact to discrete time as follows. Okay. Here is the linearization behavior, and this is the behavior of the actual system f of x. If the linearization is exponentially stable, okay, then the equilibrium point x bar is locally exponentially stable. Okay, then x bar is locally exponentially stable. Okay, the same thing for continuous time. If the linear system is exponentially unstable in the sense that you have at least one eigenvalue with what? With magnitude strictly greater than 1, because we're in discrete time. Okay, there exists an eigenvalue such that it's outside the unit circle, then x bar, the equilibrium point of the discrete time system, is unstable. If neither this nor that condition is satisfied, okay, otherwise, okay, we cannot determine the stability properties of the solutions of the system around the equilibrium point by looking at the eigenvalues or by looking at the linearization of the system. So we have to use some other means, for instance, a Lyapunov function. Okay, so if neither this nor that condition is satisfied, then the test cannot be applied. Okay, here.